Hey everyone, welcome back to the Chem 115 video help series. This is part 2 in the videos for the second section of instruction, and in this video I'm going to be talking about the basis of chemical bonding in ionic compounds. If you haven't looked at the first video and its problem set, go back and take a look at that, because that video showed you how to read the periodic table, and that is going to be essential for this discussion. Okay, cool. So, I know you all have probably already heard some stuff about covalent and ionic bonding, and don't worry, I'll summarize those points at the end. But first, I want to talk about one really important question with regards to this subject. Why does bonding happen in the first place? Now, a really good perspective to look at this question from is to look at it from a perspective of energy. Generally, chemistry, and thus bonding, happens in order to make a molecule and the atoms contained within it the most stable, and greater stability is brought about by being lower in energy. To discuss stability, I want to talk about the octet rule and how it applies to some of the most stable atoms in existence. I'm talking about the noble gases, which are found right here at the far end of the periodic table. Let's look at the simple atomic model for neon and for sodium, which, when neutral, have 10 and 11 electrons, respectively. Now, as we can recall from the last video, the electrons fill inside these shells, right here, 2 in the first shell, and then 8 from there on out, or a total of 8, which is known as the octet rule. As we can see with neon, which has a full octet, 8 in the second subshell, there are 8 electrons in that second subshell, as per the octet rule, and a total of 2 shells. As soon as there is an extra electron to consider, that electron goes into the third shell, which is new, as with the case of sodium. See, sodium has an extra shell as compared to neon, and that 11th electron goes into that third shell. It has to start over, and it's corresponding with that third period number. Now with neon, and with all of the noble gases, they have a full octet, which makes them super stable. And these elements are generally unreactive, which is why you may have heard your teacher call them inert gases. There are far fewer instances of the noble or inert gases having bonding interactions than any of the other chemicals on the periodic table. Any other elements on the periodic table, like sodium here, are far more reactive and more likely to create chemical bonds because they do not have a full octet and are not the most stable that they could be. However, through creating bonds, atoms have the ability to lose their electrons, gain the electrons of other atoms, or share electrons in order to make the atoms have full octets or becoming closer to having a full octet. This act of being closer to a full octet is what makes them more stable and is why bonding happens in the first place. This statement right here, this is a very, very important concept to know, so I highly recommend writing it down or committing it to memory. Okay, so knowing all of this now, let's go on to a discussion about ionic bonding. So, ionic bonding is when 2 or more atoms engage in a bond, wherein during the case of an ionic bond between just 2 atoms, one atom will lose one of the electrons, or more, to the other atom, which will subsequently gain the electron, or electrons, given to it from the other atom in the bond. So this statement right here is just restating what I said, very, very important to commit to memory. Ionic bonds generally happen between metals and nonmetals, which can be located on the periodic table as per the discussion that we had in the first video. Now using NaCl, an ionic bond, let's talk about energy and why sodium gives up an electron to Cl in order to participate in an ionic bond with it. Here are some simple atomic models for neutral sodium and chlorine, respectively. Recall that the most stable way for an atom to exist is with a full octet of electrons. Now, looking at the simple atomic model for sodium, what would be the most energy efficient way to have a full octet of electrons? Remember, you can only go either way, by adding electrons to the atom or by removing electrons from the atom. Remember, you cannot add or take away protons from the atom because then that changes the type of atom that it is. Proton number is what we use to identify the type of atom that it is. I'm going to give you time to think. Pause now, take a second, and I'll explain it. So, sodium can either gain an additional 7 electrons to make it a full octet, or it can simply lose just the 1 here to make it an octet. Obviously, it's just going to go ahead and lose 1 electron to get the full octet, because that's easier to do. What happens when you lose an electron? It becomes an overall net positive charge, which we can see right here. Let's do the same thing with chlorine. I'm going to give you time to think. Pause now. In a similar fashion, chlorine can either lose these 7 electrons or simply gain 1 electron to make it a full octet. So obviously it's going to gain 1 electron to make it a full octet, which would give it an overall -1 charge right here. And those two facts about sodium and chlorine is what guides the principle behind why these two can form an ionic bond. By sodium giving up its outermost electron to chlorine, it is able to exist as an octet of electrons. Both of them are. By chlorine accepting an electron from sodium, it is now able to exist as an octet as well. So the way we can think about it is standalone atoms, as in like a sodium ion and a chlorine ion. These atoms have electrical charges on them, corresponding to the amount of electrons they have to give away to exist as an octet, which would make it a positive number, or the amount of electrons that they would have to receive in order to exist as an octet, which would make them a negative number. Now, an interesting thing that we can do is we can use the groups of the periodic table in order to predict what electrical charges these atoms will have. As we can see by the periodic table that I've inserted here, group 1, which all have 1 valence electron in their outermost shell, are likely to give away 1 electron in their ionic bonds, and thus will have an electrical charge of +1 attached to those atoms. Group 2 has an electrical charge of +2 because they are likely to give away 2 of their electrons to become a full octet. Group 13, which is here, will give away 3 of their electrons to have an overall charge of +3. Then we get to group 14. This can be them giving away 4 of their electrons to become a +4, or it can be them receiving 4 to become -4. That can be either or. With group 15, they definitely receive 3 electrons, and so they'll have an overall charge of -3. Group 16 has a -2 charge. Group 17 has a -1. Group 18 have no charges attached to them. These are the inert gases, if you'll recall. So because the inert gases have a full octet, they neither receive nor do they give away their electrons. As we can see here, ions with positive electrical charges are called cations, whereas ions with negative electrical charges are called anions. This is very important to remember. This periodic table trend can be very useful in predicting ionic bonding trends, because a helpful way to think about ionic bonds is that the electrical charges that form an ionic bond must add up to equal 0, unless specified by the molecular formula otherwise. Take the ionic bond MgO, for example. Mg, here, has an electrical charge of +2, whereas O has an electrical charge of -2. When you add up the number of atoms specified by the formula, which is 1 each, we get 1 Mg times +2, which will give you +2 here, and -2 times 1O gives you minus 2, a positive 2 plus a negative 2 equals 0. In this way, we can think of ionic bonding in simple algebraic equations. This is the same for ionic bonds between more than two elements, like CaCl2. In this formula, there's one Ca, which has a plus 2 charge, and two Cls, which have a minus 1 charge each. When we construct our simple algebraic equation, plus 2 times 1 Ca, which is the charge times the number of atoms, is equal to plus 2, and negative 1, which is the charge for Cl, times 2 total Cls equals minus 2, which again is equal to 0. Basically what we're doing with our equation is we're doing the charge number of the atom in question, the number of atoms, and you just do that for each of the atoms involved in the ionic bond, which is generally going to be two different types of atoms. Ca, which is a different type of atom from Cl. This will be on our problem set for you guys to work through, so if you don't quite understand this concept yet, that's totally okay. It's just very helpful to understand ionic bonding, what atoms participate in ionic bonds, and how many, so we want to eventually understand that. Now, aside from all this, there are two broad classes of ions that do not follow this periodic trend in order to determine the electrical charge on the ion/atom, but they oftentimes form ionic bonds. In order to understand how these ions form ionic bonds with other ions, we need to memorize the common electrical charges for each of these classes of ions. The first class of ions that do not follow the periodic trend that we saw on the periodic table are the atoms from the transition metal block. For reasons beyond the scope of this class, the transition metals sometimes have the ability to form different cations, multiple for each type of element. For example, iron here has the ability to form either a plus 2 cation, a plus 3 cation, and sometimes a plus 6 cation. This is significant because iron that forms the Fe2 plus cation could form an ionic bond with oxygen in a 1-to-1 ratio, but Fe3 plus could not form an ionic bond with oxygen in a 1-to-1 ratio. This is because, as we said earlier, the electrical charges add together to form a total charge of 0 in a neutral molecule. I'm not going to speak through all of the ions and their different electrical charges in the transition block, but you should definitely memorize them. I found it worthwhile to memorize all of this table. However, you can talk with your professor about what they would like you to memorize. The other class of ions that do not follow the periodic trend are not atoms, but are polyatomic ions. While polyatomic ions are ions with multiple atoms in them, they shouldn't be considered as an atom plus another atom, but should be considered as a discrete unit with specific charges assigned to the entire unit. In the naming video, I will go over how to name them, but take for example sulfate here, which has an electrical charge of minus 2. This polyatomic ion should be considered as one anion with a singular 2- charge that is attached to it when it forms ionic bonds with other ions. This is the same way with all of the other polyatomic ions. You should memorize the names, formulas, and charges of the following polyatomic ions. Sweet. Since this video is getting too long, I'm going to put a summary page in the problem set for ionic bonding. In the next video, we will talk about covalent compounds and how the bonding differs from ionic compounds. Just as a review, we talked about why atoms participate in bonding in order to lower their energy and increase their stability by making their electrons in their shells exist as an octet, or as close to an octet as possible. We now know how this applies to ionic bonding, and how to predict ionic bonding between two elements, as well as some of the properties of ionic bonding. There are more practice problems to really solidify this knowledge in the same place as last time. See you in the next video.